Hello, and welcome to the second movie in this three-part series of transition metals and their chemistry. In this movie, I'm going to be focusing on everything to do with coordination complexes, so how they look, their coordination numbers, the oxidation states of the transition metals involved, and how colour arises in these complexes. So in the last movie, I asked, what do these complexes look like? Well, these can take a wide variety of shapes, one of which I've already shown you. For now, we are going to focus on the tetrahedral species and the octahedral species only, being formed from monodentate ligands alone, so 6 and 4 respectively for octahedral and tetrahedral. So, here on the left we see the octahedral hexa-aqua-copper 2 ion, and on the right we see the tetrachlorocobaltate 2 ion. Now, we will see that each of these have the expected bond angles through valence shell electron pair repulsion theory. Now, the naming here isn't really important as it is never really specified. It's always good to know why we call them what we do. So, for our naming rules, number 1, we state the number of ligands but name them alphabetically. So water, for example, we call it aqua, chlorine we call it chloro, ammonia we call it amine. So of course, if it's between water and chlorine, water will go first. And in terms of the numbering side, in light of our hexa-aqua-copper 2 here, I said hexa-aqua because there are 6 water molecules, or 6 water ligands. On the right, we would call it tetrachloro because there are 4 chlorine atoms. So with 5 ligands it would be penta, 3 it would be tri, 2 it would be di, 1 it would be mono. So our next rule is that we state the transition metal involved. So of course, hexa-aqua-copper 2 and tetrachlorocobaltate 2. There's another rule linked in there somewhere. We'll go over this in just a minute. But we have to state the transition metal that is involved, otherwise we do not know which transition metal is actually there. Rule number 3, we have to state the oxidation state of the transition metal in Roman numerals. So for example, with our hexa-aqua-copper 2, it will be 2, okay, 2 II. That's how you'd represent it in Roman numerals. And then tetrachlorocobaltate 2 again in Roman numerals. I'll give a few more examples of these later on in the movie. Finally, number 4, if the compound is anionic, give the 8th form of the metal. So, for example, if it's anionic and it involves copper, it will be cuprate. In light of our tetrachlorocobaltate here, then for cobalt it will be cobaltate. Iron, it will be ferrate. We can use silver, argentate, chromium chromate. There's loads of examples of these. Now with these complexes and many others, they are also going to have a coordination number. You can think of the coordination number as being in reference to how many donor atoms are bonded to the metal cation. In the case of the 6-coordinate hexa-aqua-copper 2 over here, each oxygen atom of a water molecule behaves as a donor atom toward the central transition metal cation. In the 4-coordinate tetrachlorocobaltate 2 species on the right here, there are 4 donor atoms involved in the bonding. Now what we see is that for each donor atom bonded to the cation itself, the coordination number of the complex will increase by 1. If we were to use a bidentate ligand, however, we would note that for every time a ligand attaches, the coordination number would increase by 2, as now 2 donor atoms are bonding each time to the cation, so in the bottom right case here. So labeling these up with our coordination numbers, hexa-aqua-copper 2 we see having a coordination number of 6 because there's 6 donor atoms involved. For our tetrachlorocobaltate 2, that would be 4 chloride ligands attaching on. For our hexa-aqua-nickel 2 ion, the coordination number again would be 6 for the same reasoning as our hexa-aqua-copper 2. Then for our cobalt complex here on the bottom right, what we see is that the coordination number would be 6 because there are now 3 bidentate ligands attaching. So as I said, the coordination number will increase by 2 each time one of these adds on. Now earlier I also mentioned that we have to worry about oxidation states when it comes to our coordination complexes. So when we look at our hexa-aqua-copper 2 species on the top left here, we note that each water ligand is neutral, okay, it doesn't bring any charge whatsoever to the complex. So the only thing that must be contributing charge then is the transition metal cation, which is the copper ion, and that bears the +2 charge on itself, and therefore that will be the oxidation state of the copper in this case. Now moving on to our tetrahedral tetrachlorocobaltate 2 species here. Each chloride ligand actually bears a negative charge, okay, so chloride giving you that hint there. So for each 1- charge that is contributed by these chloride ions, what we see, of course, is that this counteracts now the charge of the cobalt. So when we see the fact that now it's got a 2- charge on it, then as each chloride represents 1-, then of course the cobalt must have been +2 in this case, because otherwise there would have been no other way to get to that charge without the cobalt being +2 and the chloride contributing -4 overall to give us the 2- charge on that complex. So same sort of explanation as with the hexa-aqua-copper 2 with the hexa-aqua-nickel 2. Okay, water is neutral, bears no charge whatsoever, and does not contribute any charge to the complex. So therefore, that will leave our nickel in the +2 oxidation state again, because it is the only thing that will contribute charge to our complex. Now on to our final cobalt-containing complex. We note that each ethane 1,2-diamine ligand is actually neutral. Now, therefore, what we must say is that the cobalt is the only thing contributing charge to the overall complex, and therefore that leaves us with the oxidation state of our cobalt being +3, and therefore it having the +3 charge upon itself. Now, I've mentioned hexa-aqua-copper 2 quite a couple of times now. Here I'm also going to introduce hexa-aqua-iron 3, the copper one being blue and the iron one being yellowy brown. Transition metal complex solutions are generally coloured, but why is that? Well, primarily focusing in on octahedral 6-coordinate systems, it was such that before the ligands coordinated onto the metal cation, the d orbitals in the copper 2, for example, were all of the same energy. They were degenerate in terms of their energy. The same scenario would have applied to the iron 3 species as well. So let's focus in on that. In the +3 oxidation state, the iron ions configuration here would be argon 3d5 as a noble gas configuration. The d orbitals, again, as I have said before, are degenerate, and which is what I am showing here. Now, when the ligands began to coordinate onto the metal cation, the d orbitals of the iron actually began to split apart in energy. These orbitals would go on to split in such a way that we get a set containing 3 of these d orbitals in a lower energy degenerate set, and then a higher energy 2 orbital degenerate set. The electrons within these orbitals can now absorb some frequency of light, HF, in the lower set, and then these electrons can be promoted from the lower energy set of orbitals into the higher energy degenerate set. The light that is not absorbed, however, has all of the unabsorbed frequencies combined together. These combined frequencies are then emitted back to us as a singular colour, and in this case it will be the yellowy brown colour that we see. Although different ligands can cause different energy splittings in these orbital sets, so in the case of substituting out ligands with others, we will see a change in the orbital energy difference between the two degenerate sets of orbitals, and a different solution colour will therefore typically arise as different frequencies of light will not be absorbed and emitted back. Even though the ligands involved with the bonding in the two complexes I've shown here are exactly the same, we still note that different frequencies of light are being absorbed and emitted. But instead of focusing on other reasons to why that is, we only really have to focus on the idea of orbital splitting being the reason to why we see colours in complexes. There are exceptions to these rules though. We can take complex to copper plus or copper 1 and scandium 3. Copper 1 containing a completely filled d subshell, therefore no d to d transitions can occur, and with scandium 3, there are no d electrons whatsoever in the ion. Therefore, once again, we don't get those d to d transitions, which is what we class as being responsible for the colours in the complexes. So that brings a close to this second movie on transition metals and their chemistry. In the final movie, I'm going to be focusing on catalysis, the colours of some complexes and solutions, along with some complex reactions. Thank you for watching.